Hi, in this video we're going to prove Chinese remainder theorem about the dependence between remainders modulo coprime numbers a and b, and we'll give a constructive proof which will in turn give us an algorithm to use this theorem in practice to build some numbers with given remainders modulo a and b if we want them. So the theorem itself states that if a and b are coprime, then for any remainder Ra modulo a and any remainder Rb modulo b, there exists some integer n such that n has remainder Ra modulo a and remainder Rb modulo b. Also it says that if there are two such integers n1 and n2, then their remainders modulo product of a and b are the same. So in other words, we can consider all ab possible remainders modulo the product of a and b, 0, 1, 2 and so on up to ab minus 1. Every such remainder corresponds to a pair of remainders Ra and Rb. Ra is the remainder of R modulo a and Rb is the remainder of R modulo b. So we claim that if we consider pairs corresponding to each such R from 0 to ab minus 1, then each of the possible ab pairs Ra, Rb appears there exactly once, corresponds to some remainder R. So let's prove the first part, that if n1 and 2 correspond to the same pair of remainders, then their remainders modulo ab are the same. This is the easier part. So first we know that n1 and n2 both have remainder Ra modulo a, and from this it follows that n1 is equal to n2 modulo a, so a divides the difference between n1 and n2. Similarly, we can conclude that b divides the difference between n1 and n2. And also we know that a and b are coprime, and from the theorem we proved in the previous lesson, we know that if two coprime numbers divide some number, then their product divides the same number. So AB divides difference n1 minus n2. And this means in turn that n1 is equal to n2 modulo AB. So indeed the remainders of n1 and n2 modulo AB are the same. So we proved the second part of the theorem, that actually means that different remainders modulo AB lead to different pairs Ra, Rb. And this already actually proves the first part of the theorem. Indeed, the number of remainders R modulo AB is AB, all the numbers from 0 to AB minus 1, and the number of possible pairs of remainders Ra, Rb is also A times B, because there are A possible remainders modulo A and B possible remainders modulo B, and all pairs of them are possible. So each R corresponds to unique pair Ra, Rb. We just proved it because if two numbers have the same pair of remainders Ra, Rb, then their remainders modulo AB are the same. So if two numbers between 0 and AB minus 1 have the same pair of remainders modulo A and B, they have to coincide. So each R between 0 and AB minus 1, which is a remainder modulo AB, actually corresponds to unique pair. And the number of pairs is equal to the number of remainders. So each pair also corresponds to unique R. For each pair there has to be some remainder R that corresponds to it. Otherwise the quantities don't come out equal. So we will also show a constructive proof. This proof just says that, okay, for any Ra, Rb there is some remainder R which corresponds to this pair, but we don't know how to find it, and we want some algorithm that will find it for us to use in applications. So again, the greatest common divisor of a and b is equal to 1, and so it follows from the extended Euclid's algorithm from the previous module that 1 can be represented as sum of a times x plus b times y for some integer x and y. From this it follows that ax is equal to 1 modulo b and by is equal to 1 modulo a from this equality. So these two equalities already give us some pairs of remainders. In particular, ax corresponds to pair of remainders 0 and 1, because a divides ax, so remainder of ax modulo a is 0, and remainder of ax modulo b is 1 because ax is equal to 1 modulo b. Similarly, by corresponds to the pair 1, 0. So we have pairs 0, 1 and 1, 0. And from those pairs we can combine to get any pair we want. If we want pair RA, RB, then we can just combine pair 1, 0 with coefficient RA with pair 0, 1 with coefficient RB and sum them up, and we will get exactly pair RA and RB. Let's check that. So consider n, which is equal to RA times BY, because BY corresponds to pair 1, 0, plus RB times pair AX, because AX corresponds to 0, 1. So consider such n. And first let's see what is the remainder of this n modulo a. So n is a sum of two numbers, and the second number, RB times A times X, is divisible by a. So it is equal to 0 modulo a. So we only need to look at the remainder of RA times B times Y modulo a. And also we know that BY is equal to 1 modulo a, so we can just cancel the terms B and Y, and only RA remains. So n is indeed equal to RA modulo a. Now let's consider n modulo b, and similarly the first summand in the sum of these two terms, RA times B times Y, is divisible by B, so it is equal to 0 modulo b. And then RB times A times X is equal to RB, because A times X is equal to 1 modulo b, so we can just cancel AX and only RB returns. So indeed, this particular n has pair of remainders RA, RB, corresponding to modulo A and modulo B. And this gives us an algorithm to build integer n with the given pair of remainders modulo A and modulo B. The algorithm is the following. We take numbers A and B and we launch the extended Euclid's algorithm to represent their common divisor 1 as a sum of AX and BY for some integers x and y. And now we know these x and y. And then to compute n, which has remainders RA and RB modulo A and B correspondingly, we just compute RA times BY plus RB times AX, and we get the n we need. So this is our algorithm again.